Hello, Oscar. Hello, Mina. Today is 10/2/21. Go get a rubber band if you can find one. Please find a rubber band while I check folks in. I got my Oscar and my Mina. And I got Alex. Good. So get a rubber band, folks, for today's warm-up activity, which we need today. Good. Louisa and Feeny are here. And suddenly I have a third of my class. Love it. On this snowy JFK day. Yes, I'm in W201. Happy to be here. Chelsea, good morning. Penelope, good morning. Yeah, all right, good. So if you're just joining us, please get a rubber band. Any sort of rubber band will do. Man, people are flying in. Good morning, Lola, Alicia, and Errol. 5 to go, and we are complete. I love it. Bella's here, and Aiden's here. 3 to go. Dynamite. All right. Dynamite. So I got a rubber band. In fact, I got a couple in case I break one. You'll need one too for our first activity. And if you've got one already, we're talking about, you may have already done it, I don't know, but I think it's fun to talk about as a group. So it's on, hello, page 204. Okay, do I have anybody else? I still need a few of you. I still need 3 of you. We'll see if I get them. Hey, there's Anne Sophie. Welcome. 2 more and I'm complete. 2 more and I'm complete. Ba-da-da-ba-da-bum-bum. Let's go ahead and begin. So, if you haven't, everybody get a rubber band and turn to page 204. If you haven't done it already, we're going to do it now. If you've already done it, forgive me. So, I'd like you to turn to 204, take your rubber band and put it, without stretching it, on your upper lip. Your upper lip is very sensitive to changes in temperature. That's why when we sip something, we know if it's hot or cold immediately. We have lots of nerve cells right here. So we're going to put that on here, and I want you to then stretch it and unstretch it. And tell me when it feels warmer. So just type in a word, whether it's stretched or unstretched. One way it should feel warmer, the other way cooler. And really stretch it a bit without breaking it. And you'll notice it. Thank you, Bella, Errol, and yes, it stretches and it's warmer. So we're going to do their little table. Yeah, good. Everybody's got it. Isn't that weird? Okay, so here's the table. You got it on your paper. You don't have to write this down. Page 204. So stretched, unstretched. And we got delta H, G, okay, so if it's stretched and it feels warmer, what's the sign on delta H? It's stretched and it's feeling warmer. What's the sign here? Positive or negative? Just think back, delta H. The sign on delta H, is it positive or negative? It feels warmer. Okay, when things feel warmer, heat is being what? When things feel warmer, heat is being what? No, heat is not added to the system. No, no, no. Guys, believe your lips. It feels warmer, just like lighting a newspaper. What's the delta H sign? 90% of you had it wrong. It feels warmer. Heat is released. So it's therefore thermic. And therefore, what sign? I know I look like my cat. So, hint, it ain't positive. Aiden had it already. It's negative. Now, try the opposite again. Yeah, it's got to be, right? Because it's warming up. It's releasing heat as you stretch it. Now, unstretch it. Doesn't it get cooler on your lip? So it's taking energy from your lip, right? It's taking energy, so your lip feels cooler or colder. So down here, when it's unstretched, here I'll write the word. It's positive. Now, delta G. Without thinking about the rubber band, when delta G was something spontaneous and happens on its own. When delta G is when delta G is things are spontaneous. You'll have to memorize this at some point. Ah, there you are. Thank you, Anthony. I got one answer and I need some more. And that is right. Negative, negative, negative. So here's the deal. Okay, look at it. What does it spontaneously prefer? Does the rubber band like to be stretched or unstretched? What is it if I don't do anything? Stretched or unstretched? Which is the more spontaneous state, stretched or unstretched? Bella says my Wi-Fi is weak. I'm sorry. I will try and talk to the school. Unstretched, thank you. Okay, so if it's unstretched, then that, my friends, is negative. It's got to be negative delta G there. That's what it wants. It likes to be, that's spontaneous. And if it's spontaneous, it's a negative delta G. That means when it's stretched, it's not happening spontaneously. I got to put in energy to do it. So that's got to be the positive. Okay, now think. Remember our equation. Delta G equals delta H minus T delta S. Let's go with the unstretched. So we want this to be negative, right? Because that's this. And we know that delta H is positive for that. So that's not going to help. Therefore, what sign does delta S gotta be to make this work? Delta S, it's a mathematical question, right? If I want this, here we are. We're doing the unstretched one. If I want this to be negative, and this delta H is positive, it's endothermic, then my delta S has got to be what? Positive or negative to accomplish this. says, hold on. Okay, you're thinking. Okay, so keep thinking. I want that to be negative. That's positive. What's delta S got to be? Thank you very much. It's got to be positive. Most of you got it, including Errol and Penelope. So, isn't that cool? We can figure out the signs of stuff as it is. And therefore, if it's stretched, it's negative. Now, think of what that means. It's weird. It means if it's unstretched, there's more disorder in the molecules. Now, we can't see them because the molecules are really small. And maybe one of you's done this before. If I stretch it, there it is. If I stretch it, delta S is negative. That means it's making it more orderly. So that's more order. And the plus means more disorder. This is just to help us think. So if I stretch it, why are they more orderly? Can you tell me what the molecules might look like, especially those that had organic chemistry in 10th grade? So what do the molecules look like as a model that makes them more ordered when I stretch it? Right? It's more ordered. How might they look if I stretch this out? So what's your model of the molecules? That's why I'm really doing this activity with you. I want you to think about a model. So when it's stretched, why is it they might be more ordered? Can you describe how they might look, the molecules? That's what we mean by representation. Can you see that? Yeah, you can see that. Okay, we got any guesses? Closer together. It's not about closeness, it's about the shape. So why is this more ordered and this more random? Again, if you're in 10th grade, think about organic molecules. Why is that more ordered? What are the molecules doing? And when I do this, what do they do? I know it's not an easy question. That's why I'm asking it. So they're not really closer. If I stretch them out, what are the organic molecules doing? I got 14 good minds. Maybe I got all of you. No, I'm missing one of you, and I don't know who it is. Are they organized in rows? It's a good guess. Kind of in rows, Aiden and Errol, straighter. Yes, so both of you more or less have it. So what happens is, if it's more ordered, they're like this. Probably in rows, I agree, Aiden. But if they're more random, it's more like this. Remember that, folks, with organic chemistry? With organic molecules, they're like the little C's go up and down. And probably it's like, I don't think they're in rows anymore. I think it's probably like this. Kind of random. You know what I'm saying? Isn't that cool? So think about it. So a rubber band is unlike a lot of stuff. A rubber band, it's endothermic to make it unstretched, to make it like this. It has to take energy. But the factor that it's really disordered ends up being more important. And it makes it so that it stays in that more disordered state, which is why the delta G is negative. So it stays like this, mainly because of the great amount of disorder of the molecules. I find that really sort of cool. and so that I can make it orderly. But to make it orderly, ironically, it heats up. It gives off energy because I'm putting it now in a more ordered state. It doesn't want to do that. And ironically, it gives off energy when I do that. The delta H is negative. It's just kind of weird and fun. And you can figure it out just by doing what we did. Okay? Okay, let's see if we have any other questions. And then we'll see if we've covered the questions in the activity, page 204, or the warm-up. Okay. Amina. Not really, Amina. It has more to do with the amount of disorder as an idea. If the molecules are more disordered, that's a positive. That's a positive amount of disorder. Remember, the universe likes disorder. Okay, so more disorder. That's going to be more favored by the universe. So, in effect, Amina, this is more important for a rubber band than that whole heat thing. Often the heat thing is more important for many reactions, but not here. Here, the disorder is more important. More disorder, that's what nature likes. Delta G is negative. It's spontaneous to be unstretched, and we think as a model it's ziggy-zaggy crazy because that's very disordered. Any other questions from you? While you're thinking, I'm going to read and make sure you can answer the rest of them. Yes. Yes, you can answer the rest. We did this, number 7. Okay. So you can answer all those now, I think. So I don't think I need to do any more with you on that page. Yeah? Cool stuff, huh? All from a rubber band and your lip, huh? Yeah. Plus you get to look like a cat for a while, which is kind of fun. Okay. I want to break and do one last thing for you, with you, and that is a different page. It's a definition that I forgot to give you, but it's not hard. So can you flip in your book to page 192? By the way, once I finish this with you, then we're going to take your questions from the book, okay? But first, let's go to page 192. I love having blackboards. And the two words are kind of weird sounding. I don't know how much they're used on the AP test, but it's exergonic. It has nothing to do with a film studio, although it seems like it to me. Instead, it's more or less a decrease in free energy, therefore it's spontaneous. So we're talking about a negative delta G, okay? So an exergonic reaction is spontaneous. And Cheryl has kind of a wacky graph, but and it kind of goes down because that's the delta G, the free energy, or just G, the free energy on that side, and this is the course of the reaction. So stages of reaction. And sure enough, I'm getting a negative delta G. Okay? It's going down, isn't it? Whereas the other one, not exergonic, but endergonic, I got to always say those carefully every year. Endergonic is not spontaneous. So it's an increase in free energy. So it's a positive delta G. And so Endergonic endergonic reactions are not spontaneous. Is it lagging for everyone else? Damn it, really? Okay, not anymore though. All right. I'm so sorry. The Wi-Fi school, they told us 10 of us here could do this, and there's much less than 10 of us in the building today. So, sigh. Okay. If you lose me today completely, stay there. I'll come back and find you again and open up a new live stream, okay? So we will keep working at it. Sorry. Okay. Rule of thumb. Rule of thumb means a general rule, right? Most exothermic reactions are exergonic. And most endothermic reactions are endergonic. Can you see that? Yeah, you can see that. It starts buffering. Bomber. Thanks, Aiden. God. All right. I guess I'll do most of my live streaming then from my basement. Example, wood burning. If I burn wood, it's got what delta H and what delta G? So if I burn wood, everybody, it's got what sign on the delta H and what sign on the delta G? Yes, you've already started burning. I'm not talking about the activation energy. So burning wood, what sign on the delta H? Just type in two signs. What sign on the delta H? What sign on the delta G? Super. Thank you. Thank you, Errol. Thank you, Chelsea. Yeah, thank you, Mina. Good. All the same answer. It's exothermic, so it's giving off heat, so minus delta H. Everybody's got it. Way to go, gang. Good. And then the delta G is also negative because, of course, once I start wood burning or paper burning, it's certainly going to be spontaneous and therefore negative delta G. Let's do a fun exception, though. Rubber band. Stretching. And we can just say the stretching was negative delta G or delta H. Remember, it got hot, but it didn't want to do that, so it was a positive delta G. That's why I like talking about the rubber band, because it's an exception. It's weird. Most of the time, this is the case, all right? My rule of thumb, exothermic, often exergonic. Endothermic, often endergonic, right? So they follow the same thing we had with delta H going down. That's exothermic, and often that's the case with delta G going down. But the rubber band is the exception. Yeah? Okay. Ute. Questions from you about that? So it's just a new term for the idea of being spontaneous. So it's spontaneous. It's whatever. It's exergonic. See, even I have a hard time thinking and saying that word. But if you see it, I want you to be able to recognize it. Okay? All right. Then we have one last thing in chapter 3. Not much. But before we do that, I want to see now. Stop. Boop. Students, do you have questions on chapter either 2 or 3? This is your time to ask me. Give me a page number and what's on your mind. And I'm gonna race. I'm gonna race the rubber band first. So, what challenges have you had? And let's see if we can help you. Got any that you've marked and you'd like some help with? Okay, Alicia has one page, 188. Number 5. So please turn to 188. And let's have a look-see. The normal boiling point is 100 degrees Celsius of water, yep. And its molar enthalpy of vaporization is 40 kilojoules per mole. Okay? What is the change in entropy in the system in joules per Kelvin when 39 grams of steam at 1 atmosphere condensed to a liquid at the normal boiling point? Does the sign for the value calculate make sense? I hope it does. Okay, so here we go. The first thing we need to do, gang, is change the grams of steam to the first thing we need to do is change the grams of steam to. Thank you. Okay, so let's do that. So it's 39.3 grams of steam. Steam is water, right? Molar mass of water, just so I know you're awake this morning. Are you out there? Thank you. Good. Thank you, Bella. Thank you, Oscar. So 18.0. Now, let's not stop there. Let's go ahead before you punch that out and think about the question. So we want the change in entropy. We really need some sort of energy. So let's check this out. So I really need to use this 40. We need to have the amount that is vaporizing. Okay, its molar enthalpy of vaporization is 40.7 kilojoules per mole. Okay, let's use that too. You know what I'm saying? So let's convert the moles to kilojoules. So use your units, grams, moles, kilojoules. You know what I'm saying? So we're going to just find out how many moles to condense. I think that's what we're doing. Are we condensing here? Yeah, condenses. So 40.7 kilojoules per 1 mole, right? Can you punch that out, please? Maybe you've done this already, some of you. What'd you get for the amount of kilojoules? Go ahead and round it. Give me a value. Okay, thank you, Bella. Let's see if others get the same thing. And rounded, yeah, good rounding, Aiden, I would say. So 88.9. I'm condensing. Should this be a negative amount of heat or positive? We need to put a sign on it. I know there's not a sign in the problem because you got to think. If it's condensing, what do you think that means about the heat? So is it endo or exo? Condensing. What would you think? We're going from a gas to a liquid. So should it be positive or negative? 88.9 kilojoules. That's important. Exo, thank you. Heat is leaving system. Good. So what's that do to our sign? Thank you, Bella and Amina. So what's that mean for the sign on the 88.9? Thank you, Penelope. It is indeed negative. So now we can solve the question. The question asks for the change in entropy. So I see an equation on page 184 that looks kind of nice. It says the change in S, entropy, equals negative delta H divided by T. That looks good, doesn't it? Achtung, we need, I know I like saying that. I've been here a long time. We need the answer in joules per Kelvin. So can you change this? We can't put in kilojoules, can we? That would be what? Just so I know you can do that mentally. We need it in joules per Kelvin, don't we? And look at this, joules Kelvin. It's going to give us the answer we want. And I may let you guys do the rest here in just a sec. Thank you, Bella. So don't forget your negative. Negative 88,900. Okay, so my people, what is that? Thank you, everybody. What is that here? Which thing is that? I want to see if you're following me. What do we now have that we can plug in here? That is the what? That is the what that we found. What is it we found? Thank you, Alicia and Amina and Sophie. So that's delta H. Notice I need a negative. So a negative and a negative going to make a positive divided by this, going to make the delta S sign positive. So now look at the last part of the question. Does the sign for the value make sense? The disorder, let me think about it. The amount of disorder is, does that make sense? The amount of disorder is increasing. Is that right? Positive delta S. So it really doesn't make sense if I'm right there. So delta S should be some sort of positive. So I'm getting more disorder would be positive. It's the opposite of what I would have guessed. So when you do your explanation, and Alicia, you can look and see what they say. Does the sign value for this make sense? If it's positive, I would have expected it to be negative, or am I wrong in my thinking there? I'm asking Alicia because she might have already thought about this. I think the sign will be positive, which seems like it's increasing randomness. which doesn't seem like would be the case here if it's condensing. I think it's exothermic. It's giving off heat, so that's negative. So that's going to be negative, and it's spontaneous at 100. So it's going to be negative, negative. Yeah, it's got to be positive, I think. Thank you, Licia. Yeah, I don't know why it's that way, but I think it's got to come out to be a positive for the delta S. Mathematically, I think that's the way it's got to be. Does it make sense? No, because I think it's getting more ordered, but maybe I don't under molecules perfectly. That's the way it is. So unless Alicia says it's negative, really, I don't get their answer, Alicia. So they got 238. Okay, and they don't even have the right, we don't have the right number. Why is that? The boiling point is 100, and its molar enthalpy is 47. What's the enthalpy? What is the change in entropy in the system when 39.9 grams of steam at 1 atmosphere condensed to a liquid at normal boiling point, 100? Good gosh almighty. That's a good one to suggest. I do not get why I've done it wrong. I'm going to have to punt on that one. In other words, I don't get the book's answer. I don't see any other way to do it, and I do not get the book's answer. My apologies, Alicia and others. I don't see another way to do it. I'm going to read it one more time, which is what I do on the AP. We have the right numbers, but the wrong sign. Oh, yeah, right, of course. Yeah. So, okay, we did get the right answer. Thanks, Aiden, but the wrong sign. So that should be 373. Yeah, so that's not our final answer, is it? Thank you, Aiden. Yeah, good point. So 373 Kelvin we have to put in there anyway. So we'll get the right answer, but the wrong sign. Maybe the key is wrong. Let me think about it one last time, and then we're going to move on. Okay, so here we go. I like to read things 3 times. And if I was taking the AP test and I didn't understand something, I also give myself 3 times to read it. Okay, I'm at 100. I'm talking about a heat of vaporization, which is positive, but for us it should be negative because it's condensing. I'm reading page 184, sorry. All right, so if we have an amount that is a negative amount of heat, because we're condensing, and the question says, what is the change in entropy in the system when 39 grams of steam condense? I'm going to punt. It's condensing from gas to a liquid. The entropy decreases, so delta S would be negative, right? Okay, let's see if this makes sense. Let's think about Alicia's suggestion. The entropy decreases, so the delta S would be negative. the delta S. So it would be from more entropy to less entropy. So I'd have a bigger to a smaller number. I guess that's the way it's got to be, Alicia, but somehow it's bothering me. Let's take Alicia's suggestion as a good answer, but it's bothering me. And I'm going to leave this problem, but that's not sitting so well in my head. I'm going to think a little bit more about that. But Alicia, it's probably got to be the way you said. But for the AP test, probably not to that depth. We need to explain something. Okay, let's go on and take another question from you. So what other ones in chapter 2 or 3 you'd like to ask about? Chapter 2 or 3? When you run out, we have plenty to do, but I'm guessing you have some. I hope so. I hope so. I hope you're all working diligently in your books, because you've got to be really independent learners for this time. And then anytime you have a problem, you can write me anytime, okay? I want you to do well on that test. And this is your key. Any of these you don't understand, write me or bring them up in class. So I want you to do well. Any others that we have in chapter 2 or 3 that you'd like to ask about? Look through. Well, while you're thinking, I'm going to go to the page that I want to tell you about. Okie dokie. Going once, going twice. Strange. Often with my AP classes, I have a lot of them. Ah, good. Okay, I got one from Bella. So let's do that. Page 159, number 1. At a given temperature, the forward and reverse rate reactions for the following reaction are shown. The units for the rate constants are left out for simplicity. All right. So we've got 2N2O5 gas forms 2N2O4 gas plus an O2. Okay, the rate forward is 2.7 times 10 to the negative third times concentration of N2O5 squared, which makes a lot of sense. The rate reverse is 4.3 times 10 to the negative second times concentration of N2O4 squared times concentration of O2. I had another here, and okay, Mina, back to the other problem. Let's do this and finish this up. Could the problem be that we did negative for delta H because the equation delta S equals delta HT already accounts for the negative delta H? But that's what I don't think is the case, Amina, because there's a negative in the equation. But you might be right, because the equation is for delta S's surroundings. And the problem's, oh, the equation's for the surroundings. Amina, you're a genius. She's got it. That's the problem. So everybody write down what she said. That's it. I forgot about that. So back on that page 184, that's the problem. That's the delta S for the surroundings. We want the delta S for the system. Okay, everybody do this. Next to this in page 184, so go to page 184. Sorry, Bella, to interrupt your problem. Go to page 184, and I suggest you write an additional reaction over here. You ready? The delta S of the system, then better equal the opposite of that, better equal positive, so delta H over T. Amina, superb, good thinking. So that, I think, is going to be true, and you can write it the other way if you want, which also equals, if you want, negative Q over T. But it's really the same thing. Okay, so change the sign and make it for the system. That is totally right. Right on, Amina. Give yourself a little pat on the shoulder for me. Well done. Good. Okay, let's see if we can get some help from everybody on this one. So I got the forward rate, the rate, reverse rate. How do I get the Q, the equilibrium constant? What do I do mathematically to get that? So what do I do with the values? I got the forward and the reverse rates here. How do I get the equilibrium constant? Yeah, products over reactants, that's really what we want. So I got, oh, notice I got the products here over the reactants here. So KEQ is products over reactants. So what can I do mathematically here? What do I put where to help solve this? Let's see if some of you have done this one already. How do I get the right number? What numbers do I put where? So how have others done this? How have others done this? Here's my forward, here's my reverse. What do I got to do with the numbers? Well, no one has this one. I'm a little surprised. I got the products here. I got the reactants here. So I'm going to guess we can divide this by this to get that. Let's see if that gives us the right answer. Okay? Everybody still with me? Yeah? Okay. Products. So I got 4.3 times 10 to the second divided by 2.7 times 10 to the third. Let me just think about that. The forward rate is less than the reverse rate. So that, I think, will do it. Let's see. Exactly, Bella. So we get this already. this over this. So can we just do the numbers? Can someone check and see if that gives us the right answer? Can we just divide the two to get the equilibrium constant? Because that's what I would think at this case. I'm just looking through to see if I missed anything. It's the other way around. Did I screw up? Products over reactants. So to get the products, the reverse reaction. So the number we got here is that. Well, let's just think about it a sec. Okay, so the forward is -3, and that's less than the reverse. So my K better be not greater than 1, but probably less than 1. And if I do this, I'm sorry, it's early in the morning and I got people whacking something outside here. So if I do -2 divided by -3, that gives me a number bigger than 1. You're right. I think we've got to flip it, don't we? If I flip it, -3 over -1, or -2, so it'd be like point. No, that's right. That's right. So it's got to be the other way around. But I don't have a good rule for you. Okay, let's see what people said. Yeah, I think it's got to be less than 1. Okay, so let's think about why that is. So really what we've done is we've done the K, the small k, for the reverse, for the forward, divided by the K of the reverse. I guess it's as easy as that. So if I divide the forward K by the reverse K, I'm going to get a number that's less than 1, and that should be it. So 0.063. Now it's the big K. That's the big K, the equilibrium constant. I don't know if I've done this before, but the reasoning I hope makes sense. If the forward one has a smaller number than the reverse, then overall I've got to have something less than 1 for my big K, equilibrium constant. Yeah, that's how to do it. Okay, other questions from you on that or other problems that we'd like to suggest? Put that down, hopefully everybody can see. Hope I'm not flickering in and out too much. Any others you'd like to ask about? Because there's one last thing I'd like to do if we run out of stuff. Just giving you a chance to think. All right, I'll go to my page while you're thinking. Okay. I'll leave that. Okay, well, the last thing I want to talk to you about is page 208. And it's using K to get delta G 0 and vice versa. So it's a useful thing, and the equation you're going to use has to do with both those suckers. I think I might have given it to you last time, but I don't remember. But it's from page 207, and it's the delta G at standard conditions equals negative RT natural log of equilibrium constant. So let's do one just so you see what's going on. So let's say we got PCl3 plus Cl2. Yep. Goes to PCl5. They're all gases. And the K is 24 at 250 degrees C. Okay, find delta G at 250 degrees C. Okay, that would be a typical AP sort of question, especially for like part A or B. So more or less, you got to chug in the numbers and do the math. All right, let's do it. So we're going to plug in here. We don't know what delta G is, so that'll be a variable. So I got to go negative RT. Now for the R, it's the 8.31 joules per gram degree C. Okay, or you can use the 1 in kilojoules if you want, okay? It doesn't really matter. Okay, times the temperature, and that sucker's got to be in Kelvin. So 250 is going to be what? 523? And then times K. No, not times natural log of K. Okay, let's make sure we can do the math. So, oh no, we got it. We can do it because we know what K is. Sorry. So don't put in natural log K. Put in what K is. K is 24. So natural log of 24. So that's pretty straightforward. Let's see if we can all punch it out. So please do natural log of 24 times 523 times negative 8.31. Let me know what you get for delta G. So punch it in, make sure we can all get the same answer. Round it also accordingly to the right number of sig figs, please. So punch in when you get it. Let's see how that is. Okay, I got some answers. Okay, Amina, and she's rounded it. Good. So negative 13,800. Let's see if others get the same. Negative 13,800. She's got joules. And let's see what goes. Okay, probably got to be K here. Joules per gram degree C. No, that's per mole. Sorry, I put gram there. There's no grams for that R value. 8.31 joules per mole Kelvin. Pardon me, shouldn't be grams, should be moles. Yeah. Okay, others get the same? Yes, Chelsea got that. Aiden did. Thank you for doing that. Great. Looks good. If you want it in kilojoules, you could also just go like this, right? Negative 13.8 kJ per mole. Voila. Voila. Let's do one with the opposite. So for the opposite, let's do PCl5 goes to PCl3 plus Cl2. Same reaction. I just sort of flipped it around because that's what the book does. And the delta G is equal to 26.5 kilojoules per mole at 227 degrees C. So I changed the temperature and get K at 227 degrees C. Same equation. Delta G equals negative RT natural log K. This time the math's a little more interesting, so let's do it. So the delta G, 26.5 kilojoules per mole equals negative. Now, if I can leave it in kilojoules per mole, but what that means for the R, and it's up to you, you can put in joules if you want, but for R, I can do then 8.31 times 10 to the negative third kilojoules per mole Kelvin. So, or you can change this to joules and use the 1 in joules. I don't care. I'm just looking for you to save time. Times the temperature. Add 273 to that. Going to give you a nice number. 273, 227, 500. Beautiful, right? 500 Kelvin times what we want is natural log of K. All right, now unravel this sucker, okay? Unravel it. Get this stuff over here. So we're going to divide this by negative 8.31 times 10 negative third. I'm going to leave the units off here for a second. Divided by 500. And equals natural log of K. Once I get this figured out, this divided by that, I still got to get rid of the natural log. What's the opposite sign, math folks, to natural log? What do I got to do mathematically? What's the opposite of natural log? Hint, it's one letter. What's the opposite of natural log? Thank you, Amina, Chelsea, Penelope. So take e to the x. So if I do that, I just get k on this side. So I got to get e to this whole thing. You know what I'm saying? So do all that and then use your e to the x button, okay? So what is e to all of that? And let's see what you get. Go ahead and crank it out. See what you get for the k value, okay? By the way, for their e, so it's e to the, you should get negative 6.37 for this top thing. But you still need to get a final answer for it. So I'll wait for somebody to get the final answer. But for your, all of that should be negative 6.37. Then try and use your e to the x button. And you should be able to get the same thing as everybody else. So please see if you do. Hey, it's sunny and beautiful out. What a shock. Okay, sorry, got distracted. 0.0017, that looks good. Let's see if others get the same. Thank you, Mina. Do a little check here. Remember, K doesn't have any label, big K. So it's just a number. Chelsea got the same thing. So we're gonna guess it is correct. Good. Any other questions from you about problems? Any other problems you thought of? If not, we're gonna use our last few minutes to start chapter 4. Thank you, Anne-Sophie. We are exactly where we want to be, exactly when. So, again, chapter 4 is fairly short, and then we got acids for 2 chapters, boom, boom, then we got redox. So we got 4 chapters left. Hey, I'm down to 1 hand. That's better than a month ago. Okay, so here we go. So we're chapter 4, solubility, unless you got other questions. Okay. What things are pretty much always soluble? I need some answers from you. Give me at least 1 of 4 answers, somebody. What's something that if I have it, it's real soluble? We're talking ions here, okay? Somebody give me a soluble ion. We had several, because they're usually going to be spectators, and we need to know that they're going to be soluble. We really need it for this chapter. So give me 1 of the 4 soluble ions that we learned. Thank you, Aiden. So NH4 plus ammonium, very, very soluble, very high solubility. Thank you, Oscar. Na plus is a member of the first family. That's the alkali metals. Example, Na plus. But that whole family will do it, Oscar. Good, NH4 plus we had. K plus, Alicia, is also an alkali metal. So we got that one covered. We got 2 more I'd like you to know. One really you have to know. Have to know. No, Ca2 plus isn't always soluble, Amina. So not really always soluble. It's what the taxis have in the evening. What do taxis charge when it's dark? Come on, we had a bad joke about this. Ah, Amina's got it. So does Lola. So NO3 minus nitrate. And the last one, anybody? For the most part, it's acetate. CH3COO minus. These guys are soluble. They're highly soluble. Yeah? Okay. Ute. So they make good electrolytes. Ooh, a word you sport people also should know, right? We like to have lots of electrolytes. Okay, what are electrolytes? Electrolytes are solutions that, oh, Amina, you are quicker than I can write. She's on fire today. Amina has got it. Okay, so electrolytes are solutions that conduct electricity. In our bodies, we use electrical current. That's our nervous system. If you don't have enough electrolytes, right, like when I used to run marathons, you better drink something that has not just water, but has ions in it. I need ions to help carry the charge back and forth, right? So if I got a plus and a minus, ions can help carry this along. Na plus will go this way, Cl minus will go this way, just as an example. And if I have things going back and forth between the two poles, then that makes a good electrolyte, right? I need to conduct electricity. I have to have ions present. Cations and anions. Beautiful. Good. I think I told you this before. Cheryl likes to use for water. Likes to use that this side is negative, but she uses a delta, negative, and this side's positive, she uses a delta plus. I don't care if you use the delta, but I do want you to know that for water has a dipole. Remember, one side's positive, one side's negative. So this is a basic we need for this chapter. Ute. Okay, good. We had this word, I think, dissociation. It means breaking up into ions. Example, dissolving salt. Not an example. Dissolving sugar. Whoa, we got something against sugar? Why don't we say sugar is dissociating here? Sugar dissolves really well in water. What's my problem? Folks who were here in 10th grade probably will be able to answer this. If you're new, you may not know enough about sugar. I don't know. What's my problem? Why doesn't sugar dissociate? It does dissolve. What's the problem with sugar? And if I'm running, I can have sugar, but it's not going to give me electrolyte. Why not? What does sugar lack, people? What does sugar lack? It's got no what? We're about out of time, so I'm waiting for an answer from you. You still with me? The clock's still running. Bum, 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 ba-dum, bum, bum. What does sugar not have? It doesn't galacticity because Alicia has it, because it doesn't have any ions. It's a molecular solid. It only makes little tiny sugar molecules. All right, so no ions. Thank you, Anne-Sophie. Good. Let's stop there for today. Thank you, everybody. Have questions ready tomorrow if you got some, because that's one reason I'm here. And we're going to do more of chapter 4 tomorrow as well. Talk about solubility and all the math and concepts that goes with that chapter. Okay? Thank you, everybody. Maybe go out and get a little sun, huh? You're looking a little pale. Nothing personal. Okay, see you tomorrow.